Hi, my name is Mia Case from the College of St. Scholastica, and today I'll be discussing citrate synthase, which is a key enzyme in the Krebs cycle and which is one of the most vital pathways in cellular energy metabolism. So the Krebs cycle contains three major committing steps, and citrate synthase catalyzes the very first one. This makes it essential for energy production and sets the pace for mitochondrial metabolism. The Krebs cycle is also called the citric acid cycle, and this occurs in the mitochondria to generate energy through the oxidation of acetyl-CoA into CO2 and water. Citrate synthase catalyzes the condensation of acetyl-CoA and oxaloacetate to form citrate and CoA. It's driven by a large negative Gibbs free energy of about negative 31 kilojoules per mole, meaning it's spontaneous and irreversible. So what is this squiggly looking mess? This is the three-dimensional structure of citrate synthase. It's a homodimer, meaning it has two identical subunits, each subunit containing 20 alpha helices and one beta sheet. This forms a tight, compact structure critical for catalysis. And so, where are the active sites on these enzymes? Each subunit has one active site located between its large and small domains. The enzyme alternates between open and closed conformations. Open when oxaloacetate binds, and close when acetyl-CoA completes the catalysis. And so what molecules does it work with? Citrate synthase acts on two substrates, oxaloacetate and acetyl-CoA. These combine through an aldol condensation reaction to form citrate, which then continues through the Krebs cycle to generate NADH and FADH2. So the overall reaction is acetyl-CoA plus oxaloacetate going to citrate plus CoA. And so this step joins a 2-carbon acetyl group to a 4-carbon oxaloacetate, forming the 6-carbon citrate molecule. The mechanism begins with oxaloacetate binding first, inducing the conformational change exposing the acetyl-CoA binding pocket. This sequence ensures the reaction proceeds and prevents any unwanted catalysis or hydrolysis. So the first type of catalysis is the acid-base. The first step is where aspartate 375 acts as a base, subtracting a proton from acetyl-CoA to generate an enol intermediate. This enol is very reactive and is ready to attack the carbonyl group of the oxaloacetate. We then have a covalent catalysis step, where the enol of the acetyl-CoA nucleophilically attacks oxaloacetate's carbonyl carbon. This forms citral-CoA via the covalent catalysis. It's a condensation step that creates a new carbon-carbon bond, linking both the substrates together. Citral-CoA is right here. And so finally, we have another round of acid-base catalysis, where a histidine residue activates a water molecule that attacks the thioester bond of citral-CoA. And this cleaves the bond, releasing citrate and CoA, finally completing the reaction. So how have researchers studied citrate synthase? Well, there's been a variety of ways, through kinetic assays, X-ray crystallography, and structural modeling. These approaches have revealed how substrate binding and enzyme conformation change in harmony during catalysis. They've also looked at rat liver mitochondria and how citrate synthase reacts in these cells. And so, to effectively understand how it operates, scientists use enzyme kinetics, specifically the Michaelis-Menten model, to measure how substrate concentration affects the reaction rate. Here's an example of a Michaelis-Menten kinetics graph, where we have concentration and rate. First, I'd like to talk about the Vmax, which represents the maximum velocity of the reaction when all active sites are saturated. And that can be seen here as rate levels off as active site becomes saturated. We then have the Km, which measures the substrate affinity. Lower values mean higher affinity, and higher values mean lower affinity. We can also find it by taking 1/2 Vmax and looking at the substrate concentration. So, how did they perform these experiments? Researchers varied one substrate concentration while keeping the other constant, measuring only the initial velocities to avoid product inhibition, and this provided clean data to calculate these measures. So, what were the conditions that researchers analyzed citrate synthase? They used a physiological pH of 7.4 and 25 degrees to stimulate mitochondrial conditions. This controlled environment ensured reproducible kinetic data for accurate enzyme characterization and to find accurate kinetic data. So, what did they find? They confirmed that citrate synthase follows an ordered ternary complex mechanism, meaning oxaloacetate binds first and then acetyl-CoA. This supports how the structural changes enable precise timing and control in the Krebs cycle. They also found that the Vmax has been measured to be around 6.16 micromolar per second. And they also found that the Km values for oxaloacetate and acetyl-CoA were 1.99 micromolar and 16.3 micromolar, showing a stronger binding for oxaloacetate. So, in summary, citrate synthase initiates the Krebs cycle through precise catalysis involving acid-base and covalent mechanisms. Understanding its kinetic and structural data reveals how life's most fundamental energy process begins. Here are my references.